Greetings and welcome to Metamaterials, Engineering the Invisible. We're going to be looking into metamaterials, how they've evolved, and where their applications are today now that there is technology to actually utilize these materials. Let's get into it. Now, this is coming from a text, graduate level text from 2010. So condensed it down here to make it a little bit more palatable for the audience so we all could learn a little bit more about these materials that play a huge role in our modern life. So metamaterials, redesigning the building blocks of nature. Engineered materials with extraordinary wave controlling properties. That's what metamaterials are. They're engineered and they have extraordinary wave controlling properties. They're based on structure, not just substance. So one example we hear about a lot lately, and I think it came into more popularity after this publication of this text, was the graphene, which is not necessarily because it's carbon, but because of the structure of it. Unlocking innovations in optics, medicine, and communications. So that's where we're seeing the applications of metamaterials. All right. So what are metamaterials? As we mentioned, they're engineered materials. They're designed through microscopic structures. Their properties come from the arrangement, not the raw composition. So here we are with the degrees of order. So the properties come from the arrangement, not the raw composition. They allow control over light, sound, and other waves beyond natural limits. So microwaves, light, sound, and they enable impossible properties not found in nature. So here's an example. Is circuit boards patterned with tiny metal shapes to bend light in unusual ways. So we see a lot of these microscopic structures that are then used to do extraordinary things with other forms of energy in the forms of waves. So describing material properties. All materials interact with electrical and magnetic forces. So there's two properties here. We have permittivity and permeability. So to keep it simple here, but we'll just have to use some of this nomenclature. The Greek letter epsilon is for electrical response or permittivity. And for permeability, we use mu, or the Greek letter mu, for magnetic response. So epsilon for electric response and mu for magnetic response. So then what we get is a refractive index, N. Together, they define the refractive index. So it's you multiply these figures and do the square root. So how much waves bend and slow down. That's what the refractive index provides. So a higher number versus a lower number, trying to remember which way it goes. But either way, this index here, which taking the square root of your permittivity times the permeability, and then cancel out those factors, will give you how much the waves bend and slow down. So again, we're kind of getting a little abstract here when we talk about slowing down or speeding up, but we'll try to get a little bit more illustrative here. Now in permittivity, epsilon is how a material reacts to electric fields. So the higher epsilon, or the higher the permittivity, the stronger the slowing. So higher permittivity values cause stronger slowing of light waves as they pass through the material. So although it says permittivity, the higher the permittivity actually kind of prohibits. So it's kind of a misnomer when they call it permittivity, but it is permittivity is just expressed inversely. So the higher permittivity values cause stronger slowing of light waves as they pass through the material. The analogy here is the sponge effect. It's like a sponge soaking up water. The bigger the soak, the more electric energy is absorbed. So, stronger slowing. Let's move along. Now we're going to make sense of permeability. The permeability, represented by the Greek letter mu, is how a material reacts to magnetic fields. So the higher the permeability, the stronger the influence. Higher permeability values create stronger influence on magnetism within the material. So here's an analogy: is the sieve effect. Like a sieve letting sand pass. The more open the sieve is, the easier the passage. The higher the permeability is a stronger magnetic influence. So same kind of thing with the permittivity. We're looking at what kind of influence we can have on electricity with permittivity and what influence it has on magnetism with permeability for the most part. Trying to keep this straightforward and simplistic for our subject here of metamaterials. Then we get to what's called the refractive index, especially with optics here. The refractive index is how much a wave bends and slows in a material. As we know, when light refracts through a glass of water, and if there's a straw in there, how it seems it's bent compared to the straw we observe through the air. That's the refractive index of water being different than the air and seeing that difference. So in that combination of permeativity and permeability, in the formula we saw, the square root of the permeability times the permittivity. The analogy of refractive index is this: it's a surface change. So as a wave is passing through, it's hit something, a surface that has changed. It's like a car hitting sand or mud. It slows down and changes direction compared to pavement. Now, the thing with this analogy, it runs a little bit dry, is the fact that the car is being self-propelled, whereas if you try to apply this into what they call particle physics, the particle was moved with some initial input of energy. So as it passes through a surface change and slows down, what would cause it to speed back up when it leaves that surface? So the particle analogy falls apart there. So we got to understand it's just it's a change in the medium of what's being transferred, whether it's a sound wave, light wave, etc. There has to be a median, and that speed of propagation through there is what we're looking at here. Okay, so we get to the map of material possibilities. So there's permittivity and permeability form a map of all possible materials. So let's look at this chart over here. On the top right, we have the high permittivity, right? We have the, bear with me here, yep, high permittivity, greater than 0, and the permeability is greater than 0. So we have both are high here in the top right quadrant. This is what we call right-handed mediums. So they're impedance matching materials where they both have the same type of resistance. Most natural materials are going to fall within this range here, very at the 0 level here, or just above, let's look like just above 0 here. So what we have here is a continuum here of the relationship between the permeability and the permittivity. Now in the bottom left here, we have what's called left-handed materials. So why we call them right-handed and left-handed? The right-handed are the waves passing through in a forward manner, whereas the left-handed, they're actually backwards propagating waves. So imagine that. It kind of defies nature. So the left-handed materials, the waves, bend backwards. So it's not just the simple refraction. This is a bending backwards. Now, other zones are the permittivity is near 0, tunneling, meaning moving right through something, near 0 wave spreading. For the permeability, and perfect matching is no reflection. So, like a compass of behaviors, nature gives only a few directions, but metamaterials open the whole map. So what we have here in nature is in the top right-handed quadrant, And what we have from metamaterials is down here in the lower left-handed quadrant. And then we have the different forms of plasma. So ordinary versus exotic materials. So right-handed materials, RHM, we abbreviate it, are ordinary materials. Air, glass, water. We see normal weight behavior. The denser water that the wave slows down through, and we see the difference between the air where it is able to move through forward faster. Then we have the left-handed materials. Again, when we just express things as waves and propagation, it's propagation through a medium, whatever that medium may be, whether it's air as in sound or the ether as in electromagnetic waves. Then we have the left-handed materials. These are the engineered structures that we speak about, the metamaterials. They can actually produce reverse wave direction. So this is a historical breakthrough in 1968 when it was first predicted by the physicist Victor Veselago. And the concept sparked the idea of negative refraction. So instead of slowing down the wave as it passes through the material, it speeds up. And it takes no extra input of energy to do this. So how could this be done when the materials by nature can only provide one direction of that refraction? So, short history. In the 1950s, the Soviet scientists theorized backwards waves. As we read, the 1968, the Veselago predicts the reversed Doppler shifts and backwards radiation with negative permeability and permittivity. So reversed Doppler shifts. So instead of something as it's moving away, it would appear red shifted. If it's coming towards you, it would be blue shifted. We're seeing reversed Doppler shifts. Interesting. But the big change came in the 1990s when the advances in electronics make metamaterials real, not just theoretical. So we saw the introduction of these, and now you can start to see how there was such a big change in technology around that period. So let's look at some of the applications today and tomorrow. Invisibility cloaks to bend light around objects to hide them. In fact, this is done very well over surfaces to hide them from satellites and other kinds of surveillance by using the concepts of metamaterials. Then we have a lot of what we've been seeing more lately is perfect lenses. They surpass the natural limits of microscopes and cameras. So we're looking at lenses that surpass the limits of resolution that they should be able to attain because of the arrangement of the material itself. We have telecommunications, compact, highly efficient antennas, which are in all of our mobile devices. Think about the size the antennas used to be and how we don't even notice them today. RFID tags, cellular communications. Then there's medical imaging, sharper MRI scans, and new diagnostic tools. And of course, energy and sensing, improved solar panels, and sensitive detectors. Metamaterials are transitioning from laboratory curiosities to real-world applications across multiple industries. Again, this text was from 2010, so here we are 15 years later. So why do they matter? Why do these metamaterials even matter? Well, there's design control. Scientists gain control over fundamental properties of matter. We don't have to search for matter with certain kinds of properties. They gain control by being able to engineer them. And engineer them beyond natural limits. Natural materials are limited. Engineered structures can be tuned at will. Of course, there's lots of breakthrough potential. It promises innovations across physics, technology, and everyday life. It also provides a huge paradigm shift because it's a new way of thinking, reshaping the physical world itself. Metamaterials represent a fundamental shift in how we understand and manipulate the physical world. So, metamaterials in use. Seeing the unseen. We have super lenses for imaging. They capture details smaller than wavelength of light. So whereas normal lenses are limited by the wavelength of light that you're measuring. So if it's within the visible range, say around green or whatever, you'd pick a wavelength, and that's the limits of the details it can get at that wavelength. And you'd have to get them within a quarter wavelength or so of the proper shape to be able to really optimize that. However, with metamaterials, it can capture details even smaller than the wavelength of light. So this changes the whole elements of precision from optics. It breaks the diffraction limit for sharper resolution. The applications are medical imaging, optical microscopy, and non-destructive testing. Then there's the invisibility cloaks. Now, 15 years ago, I don't know if these were used or not, but guides waves around objects, making them appear hidden. So far, the microwave experiments have been successful. So for radar, cloaking is successful, but optical cloaking is in progress 15 years ago. So I wonder if it has been achieved. The applications are stealth technology, of course, equipment shielding from interference. Let's proceed. All right, and we're on to metamaterials in use with shaping signals. So we have polarizers. So what are polarizers? It's by filtering the waves by orientation, the polarization. So you want to filter waves, just like we were talking about with arrangement. So it's essential for optics and wireless communications. So the applications here are broadband polarizers for clear signals in reliable devices. Then there's the one we've been hearing about lately. Now remember, this is from 15 years ago. Beam steering, the direct electromagnetic waves without moving parts. So you can direct the antenna to form a beam towards a particular target. Faster and more durable than mechanical steering. The applications are for satellite communications, 5G networks, and advanced radar. Interesting. So this has been, and we have a comment here from Craig Carey. Says optical was achieved September 10th. Indeed. I've been hearing some things about that lately. As far as where we get to access it, the future is still unknown, but the future is metamaterial. Goes beyond the boundaries of natural materials. Metamaterials are redefining what's possible in science and technology, transforming abstract theory into tangible innovation, and of course, opening new frontiers in human achievement. The next revolution in how we interact with the physical world. Metamaterials, where imagination meets reality. All right, and that brings us to the end of our presentation. I hope you guys learned something here about metamaterials and how the engineered materials like this have become prevalent in our daily life and essential to the technology that we rely on every day, including pretty much this broadcast here. So with that said, I thank you all for attending this one here. If there's anything else, just leave it in the comments so we could carry on the conversation with this, as there is a quite extensive text. This is just a primer. We acquired a medal for, not sure what that is. That said, I want to thank you all for coming. Please hit the like if you haven't already. Make sure we get this word out there, and we'll see you all on the next one. Yes, you're very welcome. Glad you were able to attend. And again, the metamaterials, engineering the invisible. Peace out.